Hi everyone, and welcome to this new class in flight instruments. In this case we will continue to discuss instruments based on pressure. Right, so the first thing that we discussed before is that we usually use a pitot tube in aircraft and also a static port in order to get in one way or another the dynamic pressure and the static pressure. Okay, I mentioned before that usually the pitot static tube allows for directly obtaining the dynamic and static pressure from one same system. In many aircraft that can be used. It can also be used a different configuration, which is using a pitot tube for the dynamic pressure and a static port simply for the static pressure. Okay, this depends. Most commonly it uses two types of pressure obtaining systems in order to maximize the effectiveness of this configuration, right? So the pitot tube has a small opening at the front which allows the total pressure to enter the pressure chamber. Okay, the total pressure is made up of the dynamic pressure containing also the static pressure, as we mentioned before. In addition to the larger hole in the front of the pitot tube, there is a small hole in the back of the chamber over here, which will allow moisture in general to drain from the system should the aircraft enter precipitation. Okay, this is a way of making sure that the system operates fine in all cases. Both openings in the pitot tube need to be checked prior to any flight in order to ensure that neither is blocked, right? Okay, so what else? Many aircraft have pitot tube covers installed when they seat for extended periods of time. This is made as always as a way of making sure that the system will endure over time with no real problem. Okay, so this kind of approach actually helps to keep bugs and other kind of objects from becoming lodged in the opening of the pitot tube. Okay, right, so the static chamber is vented through small holes to the free undisturbed air on the sides of the aircraft. This is the idea of the static port. It's, as we mentioned before, a kind of a hole which is perpendicular to the flow of the velocity and which will take into, it will gather information about the undisturbed air of the sides of the aircraft. Okay, so alternatively we can actually use alternate static sources which are normally found inside of the flight deck, okay, inside of the cockpit. Now, due to, for instance, the Venturi effect, or the fact that the air inside of the cockpit is sucked to the exterior of the cockpit, okay, due to the flow of air surrounding the cockpit, it actually happens that the alternate static source, which is, as I mentioned, located in the cockpit, might have a bit of an altered, the values that we get from this source might be a bit different from the values that we would get from the static common port. Okay, now some of the effects that you might see is that maybe the altimeter indicates a slightly higher altitude than the actual. Maybe also the airspeed indicator might indicate an airspeed which is greater than the actual airspeed. Okay, or in another case the vertical speed maybe shows a momentary climb and then stabilizes in another velocity. Okay, so this is our things to take into account in the case that we use alternate static sources. Right, so this is the schematic that we saw in the previous class. I think this is pretty clear. Okay, with altitude, the distance, with the dynamic pressure and static pressure, which makes sure that both, all of these systems, which are the airspeed indicator, vertical speed indicator, and altimeter, can operate correctly. Okay, maybe they only use static, maybe they only use dynamic, but the fact that we can distinguish one to another with static ports and pitot tubes makes all of these systems able to operate. Right. So what else? What we can see here is that the airspeed indicator, which will be the first instrument that we talk about, is actually a sensitive differential pressure gauge which will measure and promptly indicate what the difference between the pitot, okay, so the dynamic pressure, and the static pressure will be. Right, so those two pressures are actually equal when the aircraft is parked on the ground, as we said before. When the aircraft moves through the air, the pressure on the pitot line will become greater than the pressure in the static lines. So this difference in pressure is registered by the airspeed pointer on the face of the instrument, okay? So essentially the ram air, because of the fact that we have a certain velocity, by the way, ram air is simply the velocity at which the aircraft is moving, the velocity of the air with respect to the aircraft, will mean that we will start getting information with regards to the difference between the dynamic pressure and the static pressure. This is all it means, okay? And basically the ISI, as it is actually normally indicated as, is the one instrument that will actually use both the pitot as well as the static system. This instrument actually introduces the static pressure into the airspeed case, while it will be the pitot pressure, the dynamic pressure, which will actually perturb in one way or another the diaphragm. The dynamic pressure will tend to expand or contract one side of the diaphragm, which, as you can see, is a mechanism which allows for expansion or contraction, okay? And because of the fact that we have this diaphragm connected or attached to an indicating system, we will be able to determine the velocity of the aircraft, right? So quickly, because we have a velocity, this velocity is converted to pitot pressure or total pressure, dynamic pressure. This dynamic pressure moves the diaphragm and the diaphragm moves the indicator, right? Okay, right, so what else? In terms of the airspeed indicator, we also need to check a bit how it operates, right? So we basically have a few elements which are essential. First, this white line over here, white arc, okay, which is commonly referred to as the flap operating range, since its lower limit represents the full flap stall speed, okay, and its upper limit actually provides the maximum flap speed. Okay, so this would be the minimum and the maximum. Now the flaps, I recommend to you, if you haven't taken the other course that I did on aerospace engineering on aircraft fundamentals and advanced, I really encourage you to take it, because I get very detailed into how flaps modify the flux moving around the wing, okay, and how the flaps are actually decisive in order to land or in order to take off. Okay, basically what we have with flaps is that by using the flaps we can get at lower velocities and also achieve higher, or high lifts. Okay, so that basically the idea is, if we're operating at low speeds, both in taking off and landing, we will be using the flaps. Okay, so this is why at lower velocity we only use flaps. We can't really operate, or we can't fly, because of the fact that the lift would be too low. Okay, and the aircraft would essentially fall. Right, so this is as I mentioned, the flap white curve. Then we have what else? We have all of this green line, which is just is the normal operating range, and we also have an upper limit, which is the maximum cruise speed, which would be reasonable to fly at. And in addition to that, we have a yellow arc, which is this over here, which is a caution range. Fly within this range only in smooth air, and then only with caution. Okay, maybe if you're diving down, maybe you get the speed might increase. You have to bear in mind that it's not recommendable. It's not recommended to actually operate at this speed. Okay, however, you can actually speed this way. What happens if you never, this line defines the never exceed speed. I think this is quite intuitive, and so we can move on. Right, so what is the next instrument? This is the altimeter. I'm sure that all of you know what the altimeter does. It measures the altitude with respect to a defined altitude. Okay, so I don't want to be redundant here, but the fact is that we get an altitude, maybe 500 meters, usually in feet, by the way, so 1,000 feet, for instance, above one specific determined level. That could be the sea level. Okay, so again, the altimeter is an instrument that measures the height of an aircraft above a given pressure level. Since the altimeter is the only instrument that is capable of indicating altitude, this is actually one of the most vital instruments installed in the aircraft, okay? We need to make sure that this instrument works, always. To use the altimeter effectively, the pilot must understand the operation of the instrument, as well as the errors associated with the altimeter and how each affect the indication. Right, so basically what happens here is that we have a stack of sealed aneroid wafers, okay, which comprise the main component of the altimeter. Now, these wafers are free to expand and contract following the changes of the static pressure. So you might remember before we mentioned that the static pressure is related to the height, to the altitude that we're working on, whereas the dynamic pressure is more related to the velocity at which we are operating, right? So which one we'll be using with the altimeter? I guess you probably, you said it right, I guess. So that's the static port, okay? Using the static pressure. Right, so again, in the case of the altimeter, we only use the static pressure, which is related to the altitude of flight. The lower the pressure, the higher the altitude, right? We already know this. A higher static pressure presses down on the wafers and causes them to collapse. A lower static pressure allows the wafers to expand. So basically what we have, as we had before, is then a mechanical linkage which connects the wafer movement to the needles on the indicator face. Right? So note that the altimeter requires an initial pressure reference so as to be calibrated. This is why the aneroid wafer is actually sealed wafer with an internal pressure of 29.92 inches of mercury. Right, so if you're in Europe, this would be 760 millimeters of high G, okay? Or another way of seeing this is 1 atmosphere. So we're basically calibrating all of this instrument as to indicate 0 when we are at 0 altitude, okay, with respect to the sea level. So whenever we go up, the pressure will go down, and so the wafers will move in a way that indicate exactly how the altitude is moving, okay? So again, the altimeter varies considerably between different types of aircraft, okay? Most commonly we will see something like this, which in this case what we have is a typical altimeter, which is graduated with numerals, okay, arranged clockwise from 0 to 9. Right, so the movement of the aneroid element, which we were discussing before, is actually transmitted through the gears to the 3 hands, okay, these 3 hands that we see over here, that will indicate the altitude. As you can guess, the shortest one indicates tens of thousands of feet, whereas the medium one will indicate the thousands of feet, and the longest one will actually indicate only hundreds of feet. Okay, so we have the longest one which is moving constantly, whereas the others will be moving at a lower rate. In addition to that, we also have what is known as the Colsman window, which is this part over here, which just indicates, as we mentioned before, the pressure at which we calibrate our system, okay? And further calibrations can be used using this calibrating knob, okay, in the case that the altitude is not correctly defined. When might this happen? Well, in the case that, this will be done using a calibrating knob in the case of having a temperature which, for instance, will have an effect on the overall pressure, right? So, as I mentioned very early, I think in the previous class, we said that the temperature is related to the pressure. So maybe if we have a higher temperature, that might mean that we have a higher pressure. However, that higher pressure is not related to a higher altitude. So we need to calibrate that, taking into account the weather of that day, usually, okay? So no more on the altimeter, we can go to the vertical speed indicator. Right. So for the vertical speed indicator, which is sometimes called a vertical velocity indicator, it will indicate whether the aircraft is climbing, descending, or in level flight. So the vertical speed indicator determines the rate of climb or descent, which is indicated in feet per minute. Okay? If properly calibrated, the VSI indicates 0 in level flight, in cruise flight, okay? Right, so the vertical speed indicators use the changing value of the static pressure again, to determine whether the aircraft is moving up, meaning that it decreases, the perceived pressure is decreasing, or either if it's moving down, in which case the decreasing, the pressure, the static pressure will actually be increasing. So, main idea. Similarly to the altimeter, it uses static pressure measurements, although in the case of the vertical speed indicators, the indication of vertical velocity is given by the instant change of pressure. It's not the pressure as it was before and then compared to later, but rather constantly visualizing or determining by the static pressure input how the altitude is changing. And from then we can actually determine how the aircraft is climbing or descending, right? So this instrument works dynamically. Again, if an aircraft is maintaining level flight and the pilot pulls back on the control yoke, for instance, causing the nose of the aircraft to pitch up, the VSI needle will actually move upward to indicate a climb. If the pitch attitude, which is the climbing rate, is held constant, the indicating needle will stabilize after a short period, from 6 to 9 seconds. What this means that basically if we actually move quickly, and due to the fact that this system is probably one of the less stable that we have discussed now, okay, what will happen is that the system will actually, the needle will start moving and will actually stabilize after 6 to 9 seconds. Right, so this is a problem because this basically means that we have a lag on determining how we are climbing, okay? So in order to compensate for these, commonly it is used, accelerometers are used in order to avoid this lag, okay? So we can actually use accelerometers which determine quicker how the change on the acceleration of the aircraft is, and by comparing the data given by the accelerometer and the vertical speed indicator, we can get a good approximation of how the aircraft is moving. So commonly in civil aircraft, especially those, I would say, cheap civil aircraft, we will only have one speed indicator, vertical speed indicator like this one. If we go a bit more advanced, we can easily, use an accelerometer to actually configure and optimize this problem, okay? Right, so this is what we can see with the vertical speed indicator. It's pretty basic. It just indicates up and down, as we mentioned before, feet per minute, okay? And again, in this case, this is what it looks like. And here we have the 6 instruments that we discussed initially, okay? This is what all the configuration looks like. And we discussed only the airspeed, the vertical speed, and the altimeter, okay? So now we can discuss the other instruments which depend on the gyroscopic effect.